Right. So today then we'll have Susmita Garai, and she's gonna show us her latest work on how to farm the earth. Susmita is originally from India, right? She did her bachelor's in the University of Calcutta and a master's in applied geophysics at the Indian Institute of Technology in Dhambad. And since then, she's a graduate student at UNM, just 3 hours from here. And yeah, she'll be showing us then the interesting work she's been doing up there. Susmita, so please take it away.
Thank you so much, Brad, for this introduction. And I'm very excited to share my research today about making Earth via pebble accretion. And I'm interested in Earth's composition and also Earth's water. So okay. So far we have two accepted accretion models. Impact.
She's cutting out for me.
Yeah, I was wondering if it's me only or
No,
it was me too.
Okay. Susmita, it seems that your connection is a bit unstable.
Uh-oh. Uh-oh. Let me see. Can you hear me now?
Yeah, I can.
Okay. Sorry, it's been a little rough today in this building, so I'll try my best. But interrupt me if it's not working. So impact-based accretion demonstrates how planets form via collision between kilometer-sized objects or hundreds of kilometer-sized objects over tens to hundreds millions of years. And one example could be collision between chondrite parent bodies or meteoritic parent bodies. Pebble accretion emerged in the past few decades as an alternative mechanism to grow giant planets because giant planets need to grow rapidly compared to or quicker than impact-based accretion models. So in this scenario, growing seed mass accretes sub-millimeter-sized pebbles, which are subject to gas drags. And in this way, you can form giant planets within like few million years in the presence of nebula. So in this slide, I will not go into detail of this slide because I just wanted to acknowledge all the work that has already been done on gas giants and also terrestrial planets. So figure A shows a plot from Lamberts and Johansson 2012 that shows that pebble accretion indeed works to grow a core up to 10 Earth's mass body, 10 Earth's mass in a few million years. And recently, Lyra et al. Shows in 2023 that even boundary regime of pebble accretion could be efficient to accrete smaller pebbles. Therefore, polydispersed pebble accretion could work from like 5 AU to like 25 AU or even more. And this way you can also form like giant planets. For the terrestrial planets, Levison et al. And also Johansson et al. Both show the dynamical possibility of growing terrestrial planets by pebble accretion. So they assume that the main growth rate of terrestrial planet is pebble accretion, and they make terrestrial planets orbit, mass, inclination, etc. Okay. I focus on Earth's bulk composition, and if I can make Earth's bulk composition via pebble accretion, okay? So I will try to tie two things together, composition and also pebble accretion. So first question I want to ask about Earth is, if we can make Earth's major element composition comprising of iron, nickel, Earth's mass from known solar system materials of chondrites is one possibility, and the next possibility is chondritic components. Okay, and then from that best fitting model, how quickly does Earth form? This is the first set of study I already have published this work. Recently, I've been working in the lab to understand Earth's water sources and volatile laws during pebble accretion, which I will show. So there are two parts. First, I will discuss the Earth's bulk composition part, and then I'll move on to the ongoing work I've been doing. Let's take a step back and look at the impact-based accretion scenario for Earth. I already mentioned that one example could be collision between meteoritic or chondritic parent bodies. Therefore, I made inversion models, least squares and Monte Carlo inversion models, where I try to make Earth's or match Earth's major element composition. And I start from different chondrites, which are here actually at the bottom. Can you guys see my pointer?
Yes, I actually have a question.
Yes, please.
Maybe I missed it. What's an inversion model?
Yes. So inversion model means I start from Earth's composition and I go back and try to find out the proportion of different input. Okay, so I have the composition of iron meteorite, sea chondrite, and all these other chondritic bodies, and I know the composition of bulk Earth today. Okay, so you try to minimize some misfit function when you try to mix them, or my model finds the best solution out of it. Does it kind of explain?
Yeah, thank you very much.
Sure. So in this case, I constrain my model by choosing the uncertainty for those elements that we observe today on Earth. Okay, that is already in the misfit function. And in figure A, I show the relative misfit on the y-axis and the composition of Earth or different elements in the x-axis. And a positive number in relative misfit means my model is overabundant in that element, and negative number means my model is depleted in that element. Therefore, we see that when I have a mixture of iron meteorite and carbonaceous chondrite and non-carbonaceous chondrites, the relative misfit do not lie within the uncertainty limit for Earth, for those elements, okay? In figure B, it shows the proportion of different chondrite bodies that my inversion models found. Now, therefore, the key takeaway from this slide is that we can consider impact-based model for Earth. However, we cannot match Earth's major element composition from chondrites or iron meteorites. Now, we do have evidences of pebbles existing in our solar system in the early history, because we have chondrites and their components, which are molten droplets mostly and early condensates. They have diameter or dimension of pebbles, okay? And they had to form within the presence of nebula. Therefore, in figure A and B, I show different chondritic components. Figure A shows a plot or an RGB map from Jean et al. 2019, showing different chondritic components like chondrules, refractory inclusions like calcium, aluminum rich inclusions, and amoeboid olivine aggregates, they're just olivines, and also matrix. And in B, it shows a plot or just a figure, just a picture from L-type chondrite showing iron grains in it. Okay, so since chondrites don't work to match Earth's major element composition, now I want to explore whether Earth can form by mixture of chondritic components, which is a strong argument for pebble accretion, because those are pebbles. Chondritic components are pebbles. Matrix is a dust-sized particle in chondritic bodies, right? So as of now, I do not consider matrix in my model. Okay, I'll show you why. Because in figure C, I show different streamlines for different Stokes number. And I have used this formula, which is a very classic, well-known formula for Stokes number, which is proportional to grain size and density, okay? So Stokes number 0.1 to 0.001 represents major chondritic components like chondrules and refractory inclusions and metal grains. And Stokes number up to like as low as 10 to the power -5 is a representative of dust size matrix. Okay, and the planet is here at the center. The blue curves correspond to streamlines for those pebbles which are for settling pebbles. So they're being captured by the protoplanet. And the red curves are just passing by the protoplanet. They're not captured. This number here shows the capture radii or capture diameter actually as a function of hill radii or hill radius, okay? So for a large Stokes number, the pebbles, which are of bigger size, like centimeter to submillimeter size, they're captured up to like 0.4, like from almost a hill diameter to 0.4 hill diameter, or yeah. And for a smaller Stokes number, we see that the capture radii is pretty small. Therefore, the implication of it is that chondrules, metal grains, and refractory inclusions, they must be preferentially captured compared to matrix, at least for Earth's orbit. Okay, so I hope I convince you why I'm not considering matrix as of now, and I'll choose the other quantity components. Now I bring back my chondrite model in the left panel, figure A and B, and now I show my component model. Component model means it has all these components: metal grains, carbonaceous chondrule, instatite chondrule, ordinary chondrule, and refractory inclusions, CIs and AOAs. And let's compare figure A and C. And figure C is the same as figure A, except for different inputs, of course, this time. And CDB and CMA models are both component model. All of them are component models, but they just have different inputs. Like CMA takes the input from Cornell Alexander 2022. And then CDB is completely based on measured quantity component data. Okay. So we see for figure C that all or most of the major elements fall within the uncertainty limit for Earth, which works quite better, a lot better than figure A or the chondrite model. Okay, in figure D, I show the proportion of different quantity components that my least square models found. Since least square and Monte Carlo both are kind of finding the same convergence rate or the same results, so I'm showing only the least square while showing the proportion of it. Okay, but it's not different than Monte Carlo. One more thing is that in chondrite model, it is mostly enstatite or EL type chondrule, focus on this big yellow region, which is my model yields like EL chondrite to be 90%. However, in component model, I find that majority is C chondrule, which again agrees well with pebble accretion. If pebbles are radially inward, then pebble accretion can bring a lot of outer solar system material to the inner solar system material, to the inner solar system. Therefore, Earth can accrete some of them. Okay. So the key takeaway from this one is that mixture of quantity components works way better than mixture of chondrites to match Earth's bulk chemistry. Now, while quantity components match Earth's major element chemistry, I did some calculation on how quickly I can grow a 0.7 Earth's mass body. I'm considering the giant impact scenario. That's why I'm not interested to make like 1 Earth mass. Okay, so it's more like 0.7 Earth mass and 0.3 Theia mass. Okay, so here in the y-axis, I have the Stokes number. In the x-axis, I have the Stokes number. But in the y-axis, I have silicate pebble, Stokes number representing silicate pebble. And in the y-axis, I have Stokes number for metal pebbles. Now, metal pebbles mean metal grains among all the quantity components. And silicate pebbles, it is a singular pebble. I mixed all the other quantity components except metal grain to represent in their respective proportion that will match Earth's bulk chemistry to create one singular silicate pebble that is in the y-axis. Okay. Now, this whole contour map with this this color scale and also this white contours, their planet mass in terms of Earth's mass I'm forming in the Hill regime of pebble accretion. The black dotted lines represent the metal fraction of the planets, okay, or of the growing planets. And I mentioned already that I am making the Earth in only Hill regime. So I'm starting from about like 10 to the power minus 3 Earth's mass. And I constrained the composition of these models to match, to start with solar-like iron silica abundance. Okay. This red dots here represents the Stokes number combination of chondrules and different metal grains. So these are calculated based on their measured density and sizes. Okay. Now I extend this red dots horizontally along the x-axis to represent metal aggregates, because metal grains can coalesce and make metal aggregates, but this here, the right hand also represents the bouncing barrier. So this is more like a hypothetical pebble that can form, right? Because beyond the bouncing barrier, pebble can fragment or break into smaller pieces. So this whole box represents the planet masses and the metal fraction of the planets that can grow from this observed sizes and densities of chondritic components. Okay. Now, this red curve, the red straight line, is our preferred model. It is the model which matches Earth-like iron nickel to silica ratio, which is 2.06. So I'm starting my model from solar-like iron to silica composition, and the outcome is an Earth-like iron to silica composition. Because remember when I said that I kind of used the proportion from this plot to match Earth-like composition. Okay, so this is our Earth. This is our Earth that is forming within this box from this observed chondrules or other chondritic components. Is there any question on this plot so far?
Yeah, I do have a few questions on this
Sure.
plot. Specifically here, the density. It seems that you're using a low density. I see here the block, like column density of gas, 1,000 kilograms per square meter. That is 100 grams per square centimeter, which is about 10 times lower mass than the minimum mass solar nebula. So I was wondering why you chose this low density nebula for this calculation, and did you
Yes.
try to change that?
Yes, I could choose as high as possible. However, considering the formation timeline of different chondritic components, I chose to use a little minimum values because chondrules kind of formed like two. It's really well debated now. It's not well agreed at all. So it can start from the zero timeline, which means the diffractor inclusion timelines, but also there are arguments that it starts a little later on, like after 2 million years. Okay, so I chose this disk parameter considering the fact that the disk perhaps evolved a little bit more. Does it kind of answer?
Right, but even 2 million years at just one E folding time, the density would wouldn't drop by a factor of 10. Of course, you know, like the minimum mass, that's not a done deal, but that's usually what we use. So I was wondering why just 10 times less. And also that has an impact on the pebble accretion model they're using, because that's impacted the Stokes numbers. And I see that you're using 10 to the minus 3 Earth mass already in the Hill regime.
Yes.
That's an object that is a tenth of the moon mass. I would imagine this would be deep in the Bondi regime. And maybe that's because of lowering the density or increasing the Stokes numbers of the pebbles. right? Whereas I would imagine that the Stokes numbers, it would be hard to get Stokes numbers of 10 to the -1 at 1 AU. I would imagine 10 to the -2, perhaps even 10 to the -3. I mean, you are considering pebbles at 10 to the -3 Stokes number here, right?
Right.
Yeah, if you only consider those, how would the accretion timescales for the Earth change? That would be a lot longer,
So,
right?
yes, it can be a lot longer, of course. Of course, if I start from a dense gas, like increase the column density of gas, of course, it will make Earth form faster.
Mm.
Yes, those are very good comments. I will take consideration of that. But also, it's a very simplistic model where I have not shown any Stokes number evolution
Mm-hmm.
that I tend to do like in another project that has been going on. Okay, but this
Sorry, maybe the gas density does not enter the problem at all.
I mean, it has to because of the Stokes number.
Yeah,
If you
but this is a parameter survey of Stokes number.
Sure, that's correct.
Yeah, so maybe the gas density is not considered at all. Yeah, just talking about how to construct this kind of model with
Yeah.
the gas density, but maybe it does not enter the problem at all.
I understand, but then if you had a higher density, you would have a lower Stokes number.
Yeah,
That would
you'll move to the
delay.
lower left plot. Yes. Yeah.
Yes, you'd move it to the lower left plot. That's true.
Yeah,
Yes.
but I don't think the caption says anything. Yeah.
Mm. All right. Well, glad that it works also with higher density.
Okay. Any further comments or questions? Okay, I'll move on then. However, it's good to match our bulk composition, but there is limitation of our composition model. If we look at the isotope composition for Earth, let's focus on figure A and B. These are plots from Warren 2011 and Lauder's 2000. These are classic plots in titanium chromium space and oxygen isotope space, showing that Earth is here, the carbonaceous type bodies are here, and NC type bodies are here. Also here, let's see, the carbonaceous bodies are here, okay? Even refractory inclusions would be way here. Their values are like -40 or so. And the Earth is here, and the NC type or non-carbonaceous type bodies are here. Therefore, Earth resembles, Earth's isotopic composition is more like NC bodies, right? So that is a problem in our model. That chondrite model, of course, I have already shown that doesn't work for Earth's major element composition, but it does match isotopic composition, right? However, component model matches Earth's bulk composition, but it doesn't do a good job for Earth's isotopic composition, okay? So in this case, I chose to run another component model, considering the fact that I'll fix my E-chondrial to be 60%. Now, you might argue, you might raise a question that chondrite and chondrials are different things, but here I chose E-chondrial to be 60% because instatite chondrite itself is like 80% chondrials. So it's mostly chondrials. So the misfit in this case in constant component model, it's better than chondrite fit, of course, chondrite model, but it doesn't match Earth very well, as good as my component model when I had no constraint. Okay, and also this fit requires way more AOAs and CAIs, so it needs a lot of refractory inclusions, accretion of refractory inclusions. So to overcome this challenge, I have said before that I'm not considering metrics so far, but one can raise a question that metrics-like material already is coating chondrials, or they can coalesce and make bigger aggregates of matrix, right? So I just wanted to see if I add matrix, does it work? Because this model that works, my best fitting chondrite model that works for major element gives the isotope values of Earth to be way less than Earth itself. Earth is here, which is, sorry, Earth is here, which is like 5 and 2, but my model is lighter. It predicts a lighter oxygen isotope values for those models. Therefore, I also need something positive, some positive input to compensate for that, right? And matrix has values which are way here, okay, like 7, 8, something like that, beyond CI, or CI is a representative of matrix actually, because it's mostly matrix. So I added matrix to it. Surprisingly, my inversion model doesn't show a big change in its proportion. So as you see, I just need like 1 weight % of matrix as my inversion model yields, and therefore the fit is no difference than my best fitting component model, okay? However, matrix requires, if I'm accreting 1 weight % matrix, it's still not enough to compensate for this isotope, light isotope composition. So I would need like up to 300 per mil values. Those are indeed seen in some matrix because it has some primitive solar grains showing a anomalously high positive delta 17 and 18 values, okay? So I can make major element and oxygen isotope composition of Earth both work if I add matrix, if I consider matrix with other chondritic components, and if the matrix has anomalously high positive delta 17 and 18 oxygen isotope values. So the major takeaways from this part of my study is that mixture of chondritic components match Earth's major element composition way better than chondrites. At least it matches within the uncertainty for Earth. This plot shows a comparison between my studies, other studies, CTB and CMA, which are those red curves, outperform all the other models. Actually exploring whether Earth can be formed from chondritic components goes way back in 1977. Study was done by Anders. And then later on, Cornel Alexander did a similar thing. And then I did a similar thing. And then I'm also plotting my chondrite model and chondrite model from Barbine and O'Brien. And of course, the component models outperform all the other models to match Earth's those 7 major elements. Also, interestingly, we find that Earth would accrete a lot of CAIs and AOAs. So those early condensates or refractory condensates are not found in, they're not found more than, I think, 13%. In some CO chondrites, you will find like up to 13%, but I think my best fitting model shows like 13 to 15%. So Earth might have accreted a lot of early condensates via pebble accretion. Earth's oxygen isotope composition matches well if we add matrix to our component model, having high or anomalously high 17 and 18 oxygen values. And this way, from the observed density and sizes of chondritic components, Earth can form in the Hill regime of pebble accretion within like 2 million years. Okay. So before I switch to the next part of my talk, I'm happy to take questions if there is any, or comments, of course.
I might have missed one point. For pebble accretion,
Yes.
you need the seed.
Yes.
And how do you determine the composition of the seed?
I have assumed that it has the same composition as Earth. Okay, so, and also I'm showing a homogeneous accretion scenario. Okay, so I have used these proportions, and then this proportion will go into the silicate pebble. How I have constrained this model, like the proportion of silicate pebble I would require to make this best fitting composition. Does it sort of answer your question?
Yes, yeah, sort of.
Okay.
One question. I think I missed the also one thing here. So
Yeah.
your conclusion is that adding matrix material to the Earth, a little bit of matrix material fixes the isotope problem, which is great. But as you were explaining before, I thought that you said that adding matrix did not. So I did not
Yes. So
fix the issue. So
when I start here, I
what's
should
going on?
say that matrix is not captured. I mean, other bigger pebbles or chondritic components are preferentially captured compared to matrix, right? And then here I say that, okay, let's add matrix composition and see what my inversion result finds. And my inversion finds that I need like 1 weight % matrix. So it's no different than the original model. If I, again, go back to the argument that preferentially capture of bigger chondritic components, okay? So adding matrix doesn't fix the problem unless it has anomalously high oxygen 18 and 17 values. So these are the conditions that would be required to match the oxygen isotope composition for Earth. Otherwise, only with average composition of matrix, it doesn't work.
All right. Okay. So you need some matrix that is high
Yes.
on these isotopes.
Yes.
Is
Yeah.
that reasonable to assume?
We're not assuming it. These are just calculated values I would need. And then I went to the literature just to see that. I mean, matrix is like a well-debated topic. We don't know how it came or things like that, but it has some solar grains, pre-solar grains that has highly anomalous values.
Right.
Yes.
And you could add that amount of matrix by planetesimal accretion, right? So mixing chondrites to the accretion in the end.
One advantage of mixing components over chondrite is that chondrites have predetermined values. Chondrites have predetermined proportion of matrix, chondrules, refractory inclusions. However, pebble accretion has the feasibility of mixing them in any proportion you want because those were early and those were free floating objects, right? Before they got accreted into chondrite. Yeah.
Yeah, if I just may make one comment here. So to answer Vlad's question, here is this isotopic composition for matrix. It looked like very unreasonable, you know, because there are some chondrules and some components of chondrites that have like layered different isotopic composition, and the idea is that these are mostly presolar grains that come from infall, and the infall is not homogeneous all the time. So you have bulk of material coming from the cloud that has very anomalous oxygen isotopic values.
Yes, I agree with you.
You can work around actually with these numbers here.
Yes, it is very diverse.
Yeah.
It is very diverse. Matrix show a very high range, maybe very broad range of things. Of course, I agree with you.
It's very possible that at some point, at some epoch, you got a very high oxygen isotopic composition matrix that were accreted.
Yes, yes, yes. That's a very good comment. Thank you. Okay, now I'll move to the second part where I'm interested to see the water formation for Earth. So in the left-hand side figure, I show a plot from Olson et al. 2022. In figure A, he calculates the Earth's mass, planet mass relative to Earth's mass as function of pebble accretion time in the x-axis. And 0.7 to 0.75 Earth's mass forms like in 5 to 6 million years. This rapid growth of Earth-like body will lead to very high atmospheric temperature. So in figure B, I show the altitude as a function of planet radius. And in the x-axis, again, I have the pebble accretion timeline. And these white contours show the temperature in Kelvin for those rapid growth, rapidly formed bodies during pebble accretion. In figure C, this is again the temperature. However, this is the internal temperature of an ongoing planet or on-growing planet. In the right-hand side panel, I show a schematic from Sharp 2017, where he introduces the nebular ingassing of different volatile species. So the idea is that as the planet grows rapidly in the presence of nebula, it attracts a huge hydrogen-rich atmosphere from its surrounding. Therefore, the pressure goes high, up to like 10 to 1,000 bars. Of course, the temperature goes high. That's also calculated here. And therefore, the essence of it is that my chondritic component pebbles, they're bringing iron oxide in their silicates. So therefore, in the presence of hydrogen gas, when they're accreting, the pebbles should melt, and their iron oxide should react with the hydrogen gas. Therefore, this reaction would occur that will produce iron metal and water. Now, this is a planet scale, a very big scale process. I have conducted laboratory experiments to replicate that process at 1 ATM. This is a very simple experiment. I have used a silicon carbide furnace that is shown in, a schematic is shown in figure D, and started with MORB, which is from the East Pacific Rise in figure A I'm showing. And then I just heated that MORB, 100 milligram of MORB for like 1 to 3 hours in 1200 at 1200 to 1300 degrees C. I chose these temperatures because 1200 degrees C is theoretically below the liquidus of MORB, and 1300 degrees C is above the MORB liquidus. Okay, so this represents the partially molten versus fully molten MORBs. I made little tungsten baskets, which goes here, and then I hang this sample. I fill it with like 100 milligram of MORB charges, and then I hang it from the top, and the gas goes from the bottom. Okay, and first I run helium gas as a null phase, also just to dry my MORB out, because MORB has some water, like 0.7 weight% water. It can vary, but for my case, it was like 0.7 to 0.8 weight%. And then I heat the same sample again in the presence of hydrogen gas. Okay, and this is how my charge looks after the end of the experiment, which is like 2 millimeter in diameter. Okay. Now, these are the results and some images. There's some backscattered electron images. So the essence of these images are that anything appears brighter in one image. I mean, anything appears brighter has a higher atomic number than its background. So if we focus on, say, figure B here, this is brighter than this black thing. So this is the silicate part, and these are my iron metal that formed in the presence of hydrogen. Okay. In the presence of helium, nothing happened as we expected. So this is a null experiment, and we see no metal formed. It shouldn't. But in the hydrogen phase, yes, metal formed. This is figure C is just another, I mean, this A and B are a top view. These are superficial views. Figure C is just a vertical cross section, so showing that the metal formed are on the surface, they're in the interior and everywhere. While they're on the surface, because there are two forces playing on the metal balls. First is gravity, of course, they should sink because they're heavier than silicate. And second thing is the surface tension of those metal balls in the silicate. And the surface tension is definitely winning. That's why they're not sinking down yet. But I have seen metals sinking in the interior when they have grew up to some size. Okay. And A, B, C are for 1200 degrees C, and C and D, E, F are for 1300 degrees C, but showing the same things, those beautiful metal balls nucleated on the surface in the presence of hydrogen. Now, I want to know the composition of different melts, initial MORB and different melts and the composition of these metals that formed. So I have conducted electron microprobe analysis for all the samples here. I'm showing just one. In the y-axis, I have concentration in melt in weight percent, and in the x-axis, I have concentration in MORB in weight percent. Therefore, this line with black diamonds show initial MORB composition, and anything above this line means that melt is enriched in that element. Anything below this line means that element is depleted. That melt is depleted in those elements. So here we have 5 things. Let's focus one at a time. So as I said, this is the initial MORB. Now I reacted it with helium, right? So nothing happened. So it is just a homogeneous melt. That is the red diamonds. And it overlaps with the black diamonds, except for zinc and sulfur. That means they're lost when I heat it in helium. Then I have reacted the same sample or melted the same sample in the presence of hydrogen. Now I have 2 parts, silicate and metals. Okay, so the silicate part is represented by this green diamonds. Okay, so they also more or less overlap with the red diamonds, except for iron, because we would expect that. In this case, this is iron oxide, but I have just calculated how much iron is there. So this is expected because we are expecting some iron oxide reduction. Therefore, of course, this should be reduced like this. In this phase, the silicate should be reduced in iron oxide or iron. Now I have 2 types of metals, as I have shown here, right? One is on the surface, and there are some in the interior. So I have superficial metals and interior metals in those blue and light blue. So all of the metals, they are depleted in these elements like potassium, titanium, everything. Enriched in iron. Indeed, those are iron metal, confirmed. Enriched in phosphorus. Okay. Chromium, chromium was really present in a very small amount. I don't want to argue about that because it is, I think, below the detection level. But phosphorus, this is a repeatable outcome of my experiment over like 10 samples I have analyzed, or experiments in different conditions. Tungsten here is coming from the tungsten basket because tungsten is siderophile. Therefore, it is inevitable to have some effect on it. So that's why they're partitioning with metals a little bit. So iron and phosphorus, they come together and make alloy in my experiments. And then zinc and sulfur are lost in my experiments. Now we are super interested in the effect of phosphorus.
Your question on the previous plot?
Yes, of course. Let me go back. Yeah.
Yeah, so this black line here,
Yes.
is this the bulk composition?
This is the bulk composition of initial MORB that I have used. Yes.
Okay, and this is like, I mean, what does it represent? Does it represent the initial all terrestrial bodies? Can you tell me about this composition a little bit more?
So I have, yeah, of course. I have chosen this MORB from the East Pacific rise. And this is a volcanic glass, of course. And I have chosen that because that has like, it's easy to get MORB, you know, basalt is the most abundant thing on terrestrial bodies, at least for Earth. And it has like 13% FeO, which is a good candidate because I'm interested in FeO reduction. Okay. So that's why I have chosen this composition because it's abundant in FeO and it's easily accessible.
So if this line is, for example, if this line is the bulk composition representative of all the terrestrial bodies, basically.
No. This line is just the MORB composition. Okay.
Okay.
These black diamonds are MORB, and I have just I have just drawn a line through it so that I can compare that how much like in those materials, those elements, how much they got depleted compared to the initial composition or enriched compared to the initial composition.
Yeah, so this is this is the one-to-one line, right?
Yes.
Between the abundance in
Yes.
the sample as it after it's heated and at room temperature, right? So if the heating does nothing, it stays there,
Yes.
right?
Yes. Yes.
Yes. And the
Yes.
Morb, if I understand it, that's mid-ocean ridge basalt.
Yes.
So that's sampling the composition of Earth's mantle or lithosphere, or right?
Yeah, it's from the ridge systems where the plates diverge.
Right.
Yes.
So
So
that's
coming from the mantle, of course.
Yeah.
Yeah.
So that reflects Earth's mantle.
I cannot. I mean, it depends on which depth you are talking about, right? If you go
Yeah.
deeper, it's not basalt.
Yeah. Upper
Yeah.
mantle.
Upper mantle. Yeah.
Okay. Okay, I'll come back to this plot later on.
Okay.
Go ahead.
Okay. Now, we were very interested to see the phosphorus effect on iron metal produced. And this, I'm just bringing back, we have already seen this plot, and we were just wondering why those are spherical, right? Because iron melts at like close to 1600 degrees C, and my temperature, experimental temperature, they're never above 1300 degrees C. Therefore, I just wanted to see that what kind of crystals or melt or partial melt phosphorus is creating when it's partitioning with iron metal. So these are my data, these red ones. And these are the phosphorus abundance in various experiments in weight percent. Okay, so I'm following this one. So the key point of this phase diagram is that since they are molten, we are still working on it. So feel free to pass comments or correct me if I'm wrong. So the best idea so far we have is that they're molten, these metal balls, they're spherical, because the initial or a newborn iron metal has a lot of phosphorus because it has to be beyond this curve, right? Somewhere here. However, as the iron metals, they are coalescing with each other, growing into bigger metals, then it's becoming partially molten, or it shows different kind of lattice structure of iron. Okay. So perhaps in the initial, in a new, very, very small, tiny newborn iron, the iron phosphide, the phosphorus abundance is way more than what we see after like 1 or 3 hours. To test that hypothesis, also, we have phosphorus-free synthetic Morb that is just made in the lab. And we expected to see no metal spheres, no spherules, no symmetrically spherules. Indeed, we do not see them. We see these crystals, which are hexagonal cubic packed iron metal. Therefore, the key takeaway from this is that phosphorus is partitioning with iron, and it is lowering the melting point of pure iron metals, leading to phosphorus iron phosphide spherules. In contrast, without phosphorus, iron metal would be crystals, just like this. Okay, any questions from this slide? Okay. I was also interested to see how much water is produced and what happens to the water that is produced in this whole reaction. So this is a similar experiment I have done, but in a different setup. This is an induction furnace. And in this case, I have a quartz tube. And here I have molybdenum crucible. And I have used Morb and fill this with Morb. And then my gas flows from the top. This is a sealed system, okay? My gas flows from the top and my water comes out from the bottom, and I just collect it with liquid nitrogen cryogenically. And then I measure the mass of that water that is produced in the presence of hydrogen, just to kind of calculate how much FeO is reduced, because arguably all the water is coming from FeO reduction. That's how it's a measurement of how much FeO got reduced in the melt in different times. And also then I have measured the hydrogen isotope fractionation between the produced water and the input hydrogen gas. So figure B shows in the y-axis I show the hydrogen fractionation coefficient as a function of time in the x-axis, temperature. And these temperatures are the maximum temperature I reached during my experiments, okay, for different masses, as I show here. This black solid line is the equilibrium curve. And when I say chondrule, actually, this is a misleading term. I should say chondrule-like, because I wanted to start from different composition, and I wanted to choose a chondrule, but it's hard to get a chondrule. At the same time, it has a very high melting point, okay? So chondrule is ultramafic. Therefore, I just had my pre-existing morph, and I just mixed it with olivine to create a picrobasalt type or chondrule type composition, more or less, which is ultramafic, and the ratio is 1:1. Okay, sorry for that misleading term, but this is chondrule-like. So the key point from this curve, or from plot B, is that the water is reaching equilibrium, and it is just overlapping with this theoretical plot. The morph initially had some water. If I have plotted those fractionation numbers, that would be way up here. However, I have extracted all the water when I run it with helium. So this is purely coming from FeO reduction. This water is purely coming from FeO reduction. So the pebble will equilibrate with their local hydrogen atmosphere when they're falling through the hot atmosphere of the protoplanet. Okay. So I have interesting takeaways from these experiments I have been conducting. The first one, I have already mentioned that chondritic components, accretion of chondritic components matches Earth's bulk chemistry. And I have calculated how much FeO I'm bringing this way, right? So my Earth has I'm bringing 1 weight % more FeO in Earth through this process. And indeed, they should melt in the atmosphere, which is hydrogen and helium rich. And therefore, this way, FeO reduction will form Earth's core-forming metal, mantle-forming silicate, and water. 3 major things for Earth. Now, if I reduce all the excess FeO I'm bringing via pebble accretion, it will make 10 ocean masses of water on Earth and 3 weight % of the metal that should contribute to the core. The remainder of the core mass, of course, will come from metal grain, because this FeO silicate is only in silicate chondrules and refractory. They have a little bit refractory inclusions. My experiment shows that iron phosphide is produced via this reaction. Therefore, phosphorus might be it may enter the core during pebble accretion. I mean, I think people think that for iron sulfide is the first phase that goes into the Earth's core, not phosphide. Therefore, a little bit of phosphide might have a lot of implications for the Earth's core during pebble accretion, or followed by pebble accretion. Pebbles will reach equilibrium with its local atmosphere while accreting, and sulfur and zinc are lost in the atmosphere in this process. So these are my overall takeaways, and I'm happy to take more questions or comments.
Excellent. Thank you very much. We have questions now. Stanley?
Yeah, just a quick one about these experiments you're talking about. It seems like they're all taking place at atmospheric pressure.
Yes.
Correct. Do you expect any differences in the results at higher pressures?
Yes. For the higher pressure, I'm interested to know how the oxygen fugacity will play a role in that, right? Because it is a function of the water that is being produced. Okay. And since the pebble is reaching equilibrium with the atmosphere, that means the rate will change at higher pressure, right? I mean, whatever is coming out of a pebble, because it's melting, reacting at a higher pressure, you can think of this as like going back faster than 1 atm, right? So I have not conducted at high pressure, so I cannot arguably like make any bold statement about it. But of course, I think it will show perhaps more like more segregation of phosphorus, and sulfur is lost. I tend to run an experiment without helium because I'm losing all the sulfur in the presence of helium, like before even I started reducing it. So perhaps sulfur could go as well with iron
At higher pressures.
at higher pressures. Yes.
Yeah, I have a question. If you can go back to that plot.
Of course.
Yeah, so it seems like your material. So just one identification is that everything from this iron to all the way to nickel, these are all moderately volatiles, right?
Yes.
We call them.
Except titanium, magnesium, they're refractory.
Yeah, so there are like sulfur, zinc, nickel. These are all moderately volatiles, and you have these depletions. They're the depletions of the MVEs, which are actually shown in all the terrestrial bodies, to be precise, not exclusive to Earth only. So in that case, is it possible? Like, do you think that even before the parent body accretion, the process contributed to that depletion, and then there are several other processes that actually made that depletion more or changed it in some way? Is that possible? Like, is a combined effect? Because we know there were some depletions, or the depletion that is shown in all the terrestrial bodies are present, and that is because of the nebular process. So any comment on that?
So I have a thought on that. It's a complicated process, as you have addressed. It's like a mix of everything.
Yeah, absolutely.
In this experiment, I'm trying to replicate what is happening if this is the Earth's surface and its atmosphere, and the pebble is just falling through the atmosphere. It's like a pebble rain, right? Now a lot of things will happen. I'm showing what's happening here in the midair. It will go through the magma ocean. That is another thing, evolution, chemistry, and dynamic evolution of those melt, right?
Yes.
That is one thing. There could be loss from the nebula itself if the pebble is at a higher atmosphere, like, way above the surface. There will be loss from the nebula, into the nebula from the planet's atmosphere. So those two things could lead to like a different mechanism or terrestrial fractionation, especially when it's going deep into the magma ocean. We must track the evolution of pebble as it's sinking with this composition and how it's going to change.
Yeah, so I think it will be very interesting if you can show that, like how much you are getting the depletion and compare it to, because there is, if you start from Cassen 96, Chesla, even we have a paper, so we have those MV depletion curve. So you show that what is your final depletion profile based on those curves, then it will be easy to identify what are the processes that happened terrestrially before accretion, after the parent body accretion, that actually contributes to the total thing.
Absolutely. That is, we have been
Sorry to interrupt here, but we have reached the hour. I will just say that if people want to continue in the Zoom call, you are welcome to, but feel free to leave. And Susmita will be here with us for a little longer, since we are also going to upload the paper to the archive.
Yes.
Yeah. So feel free then to, if time is short for you, but please continue on then with the answer.
So yes, absolutely. We have been working on it, and as you know, there's a lot of effect as we go deeper. Temperature will increase, pressure will increase. Then again, if I consider the giant impact scenario, nothing will change in the mantle. Perhaps it's just an addition of two different bodies, mantle from two different bodies, but core will equilibrate with each other, right? So it depends on the efficiency of core merging. We have been working on it, and that's a really complicated problem, I must say.
Yeah, absolutely.
It's like there are many parameters, key parameters. Like it will also depend on how big the pebble is itself. It's like, yeah.
Thank you very much. Excellent work. I really like it. The laboratory experiments, we needed them more in the field. All right, so let's give another round of virtual applause to Susmita. And with that, then I'll stop the recording here now.